Okay. Like I said, what he's talking about in there about beats is an effect of what happens when two sine waves are put one on top of another when their frequency is very close to each other. So what I've got here, first of all, let's go back to the start. I've got a sine wave, two sine waves, the blue and the red one. They're in phase, they're slightly different amplitudes, but I don't think anyone would be particularly surprised that if I add these two things together, I get a black one. So where it goes 1 and 3, we will get a 4, and the high points coincide. The thing he was talking about with beats, though, is if the frequencies are ever so slightly different, you start getting this weird pattern with the black line, and I'll just highlight the black line now. That over time, it starts off large, then the amplitude goes low, and then it goes high. And if you get the frequency, the relative frequency right, you can actually get it to disappear, go really loud and really quiet. I haven't got this one set up so you can do it. But that black line near the middle here is high, but then when you get out this far, it's quite small. It's actually less than the blue line. So that's where you get the woo, woo, woo background to the sound you're making. That's beating, and that's when frequencies are not coinciding. What we're interested in is what happens when you combine sine waves with the same frequency. So what I can do is I can combine these two together and we get a nice sine wave. But what often people are not... actually, I'll ask the question. What do you think will happen if I move this red sine wave out of phase? So if the two, blue and the red, if they're not going up and down together, are we going to get something completely chaotic with the black line? Are we going to get something highly predictable? Are we going to get this beating system again? I'm going to move this red line. Actually, if I hide that, I might be able to bring it back in a minute. So I'm going to hide that. So if I move the red slightly across, and now add the red line and the blue line together, what do you think I'm going to get? Am I going to get something very predictable? Am I going to get something highly chaotic? Am I going to get something a bit like the beating mechanism where it goes on and off, or high and low?
Is it the beating?
You reckon we're getting beating? Oh, Jess?
Beating mechanism.
You reckon we're going to get another beating one? Let me show you. Because this is the bit, and it is a surprise to most people. Well, I don't think I even realised what it did when I first saw it. That black line, is it nice and predictable or is it beating? All the way out?
Predictable.
What's it predict? What is predicting it's always going to produce then? What are you seeing with the black line?
I don't know, it's shifted.
It's shifted, but what sort of thing is it?
Not sure.
Well, what have we called the red one? What's the blue one called?
Are you asking what
Yeah, what are all these curves called? That one is a
cosine graph?
right, sine, cosine. It could be either, because remember sine and cosine are just shifted versions. Blue one?
Also cosine?
What about the blacky green one?
Also cosine?
Yeah, that's the surprising part for most people on this, is that if you combine two sine waves or cosine waves or various forms of them with the same frequency, it doesn't matter what the relative position of them are, the phase. Add them together, you will always get another sine wave. It's actually a result of some of the stuff we were doing last lesson, and we're going to use that in a minute to produce these effects. So let's move that back. Now I'm just going to talk about the practical upshot of this. this blue line represents what's happening in the main power system for an electrical company. Okay, so this goes all over the country. It's connected to lots of different power stations, and they are producing this amount of power, and it goes in a sinusoidal wave. And we are talking about power, not voltage. Okay, so the power is being generated in a sine wave. You put a new bring up a new power station. Now we need it to match the frequency, otherwise we're going to get this beating effect and people's electricity is going to go all over the place. So there are actual quite easy mechanisms that they can use to make the turbine here spin at the same frequency as the mains. What they can do is they can put a little, feed some of the mains power into the turbine, and it will cause it to actually spin at the same speed, therefore generating the same frequency. But have a look at that size piece of machine. How easy do you think it is to get a machine that big to precisely match the highs and lows of our electrical power system, which goes high and low 50 times a second? Is it an easy job or a hard job?
Quite a difficult job.
Yeah, and that's the problem. Is what they've got is they've got a situation like something could be like that, where the power they're producing isn't in phase with the main electrical power, which means we're not getting the best power output we can get. And if you go really bad, basically this is effectively creating nothing for us. All this power is going to moving that frequency, move that back a little bit. Okay, so getting this to tie up with the main power is quite important. What they do is they actually, before they generate, they add these two together, they generate another line. They actually have two, and I've got this one slightly out. Oh, there it is. So there's a dotted line, which is another sine wave. I've got a sine wave with a 0.5. If I turn off the black one again, yeah, we'll need the blue one because that's what we're trying to match to. So there's the power we're generating from the big turbine. Here's our secondary turbine creating another sine wave. And if I can, this smaller turbine, if it's small enough it's not generating my main power, I can use that and change its speed to get it to move the output. See the dot and dash line, that one I'm highlighting. As I change the phase of this control line, I can move the phase of the generated line. So I'm doing nothing with the generator. The generator is just turning out its power, normal speed. But I'm using a second, much smaller generator that I can control what phase it's going in to actually create a new high and low. So now I've got the output from those two generators combined gives me this curve here. So I'll just hide those two. So that control line is now forcing this to move. So I'll show, well, I said I want to hide it. I don't want the label, I want to hide that. Oh, it's because it's under one of them. Okay, so as I move the phase of the control line, I can change the main power phase being generated. Yes, I will lose some energy out of these two, but when I actually go back to looking at my main power, that one, I am going to get about the best output I can from my generator. Okay, so as I move this, I can actually get a control where I can get a maximum amount of power out. And that's purely by controlling this much smaller wave. I can make this build up and give me the best possible output I could get. Okay? That's what it's actually used for. What the maths we're going to do, they actually do this sort of maths to make things line up so that the power being put out from a power station is in phase and of the same frequency as the power in the electrical grid. And that then means that we're working as efficiently as we can. It's not 100% efficient because the power generated here often is wasted. But this power is nearly all used now because we've got 1.5 on top. In fact, we've almost got a perfect one here because they're quite closely in phase. So this isn't quite 100% power, but it's very close to it. All right, with the basic idea now that we're getting, the result of this is if you add two sine waves with the same frequency together, you will get another sine wave that add two sine waves together with the same frequency, you'll get another sine wave which has the same frequency. All three will be slightly out of phase. Okay with that? Okay, so all we're talking about is the pattern this makes. So I just want to grab the functions, not from that one, from this one. I forgot to grab these earlier. What we need are these two equations. So I'll come down below, paste them in. And basically what these mean is we can actually do all this maths with both sine and cosine functions. In exam questions, they may say, give me a cosine function, which means you'll need to use the second equation. Sometimes I'll say use the sine function, which means you need to use the top one. So what we're going to do is analyze this sine function one and create something which has an amplitude. So I've got sine function, so sine of some value x plus, and I'm going to use phi, which is my phase. This causes something called a phase shift. This is actually just the general function. Value. If you're actually talking about power generators up there, in the power generation mode, x would actually be some frequency times time. Okay, so that's how this gets built into here. They can't control the omega t, but they can control the phase. So we write out the equation with a little bit of a gap. So we've got sine of x cos of phi, because I'm not going to keep using the brackets on this form. I'll do that. Plus, because this is the sine one, cos of x sine of phi. Okay, so there's my two functions. What I can do is I can also multiply through and get the amplitude correct. So this is the unfortunate thing about using that A notation in the identities, is A now is the amplitude of my final sine wave. So the amplitude of my curve, I multiply both lots by A. Okay. Now, what this means for me is I can have two functions and I can calculate a number of bits from them. Oh, where's my example one gone? Keep losing it. So we've got that one. What's that one? That's the wrong one. Moved it back in place. There we go. Where did they write it? So we're going to use an example to work out how does all of this come about. And what we're going to have is we're going to be asked to express the following two functions as a single, is it sine they go for on that one? Yeah, sine function. So I've got two functions first of all coming in, one which is 4 sine of theta plus 3 cos of theta. And I want to write that in the form of a value of sine theta plus this correcting phase. And I need to work out what they are. Now if we look at them and think about squaring both sides, if we were to square both sides, we'd get a squared and the sine squared of my function is equal to 4 squared sine squared plus 3 squared cos squared. And this actually leads us to a conclusion. Actually, let's do it properly. Let's do it properly. I'll do it properly rather than skirting around the values. So my sine x is that sine theta there. Cos x is that part here. We've got our x, our theta and phi's. So this means that my value of a can be calculated by using a times cos phi. For those two to be the same, this must equal my value of 4. So looking at that piece, a cos phi is my 4. Look at the second side, or the second part. 3 is a times sine of phi. Okay. I've got sine and cos of the same angle. Well, how can I combine these two things together? Well, if I was to square this side, a squared cos phi, and square that one, I've got a common a squared that if I was to add those two equations together can be factored out. So a squared is cos squared phi plus sine squared phi, which I hope you all realise is 1. That is the same, if I took the other side, of taking the 4 and squaring it. So there's equation 1. Come on, where's it gone? So there's my equation from the left-hand side squared. And when I do the right-hand side, the second one, I get plus 3 squared. And that's my equation 2, which I'll do in blue. And the result of this is the bracket is 1. Standard identity, yeah? So we get a squared times 1 is equal to 3 squared plus 4 squared, 16 plus 9, which is 25. So the a squared, or a, my amplitude, will be a 5. I've calculated the amplitude of my sine wave, and it is always by using Pythagoras' theorem. This always, because we use Pythagoras' theorem here to create that identity, we can always do Pythagoras' theorem on the coefficients. Okay, as long as we've got the sine and the cos, and they will be in both forms. The second part is, again, back to this equation. I don't want to know what a is, I would also like to know what phi is. So this bit first led to phi, to a. And to get phi, what can I do with those two equations that will give us something sensible? We've got the red and the blue equation at the top. How can I combine those two so that I get one function? I don't want a in there, but I can get phi.
Replace a with phi?
Yep, that's going to disappear for us anyway. What single function can I get from cos phi and sine phi? What's the relationship you know that's to do with sine, cos, and one of the other trig functions?
You want to turn it into a tan function?
Go on then, let's try turning it into a tan one then, Richard. Let's see what happens. How are you going to do it?
So sine over cosine?
Yep, so we're going to put the blue equation over the red equation. A sine of phi and 4a cos of phi. So now when I go through and I cancel it, my a's are now cancelled, and I'm left with tan of phi is 3/4. So I can now use my arctan function to work out square root of the tan of that angle, which is it working it through? No, it doesn't. I'll do it on my calculator then. Shift 10.75. Actually, I'll do it on the screen one, because I can then remind you to do one thing. What things should I be careful about when I'm using theta and phi in my angles?
Make sure that they're either in degrees or radians.
Yeah, and check what you're in for the question. So some questions will work with degrees, some questions will work with the radians. So I'm just going to pull my calculator up. So I cleared down my desktop ready for this lesson, and I cleared down a load of things that I had open ready for it. So there's my apps. Maths. Calculator. There you are. There's my calculator. I'll give you a big screen so you can see what I'm typing. First thing I'm going to do is make sure I'm in the radians mode. Radians 2 there. And I want to do shift tan of 0.75, 3/4. And that gives me phi is 0.64. 3 significant figures is generally a good rounding figure. So 3 SF. That's generally what they would expect for angle in radians. If it's an angle in degrees, I would always recommend doing to 1 decimal place rather than saying 3 significant figures. You can get weird, accidentally make wrong conclusions if you use 3 significant figures and degrees. So the final part of this is to say I can now write this function, the 4 sine theta plus 3 cos theta, as A is 5, sine of theta, because that's still the angle that's changing, plus 0.644 radians. And that is the same as a function with 4 sine theta plus 3 cos theta. And I'll show you that on my GeoGebra on a fresh screen. Turn the grid on. Just do object properties. Hey, give me my grid. Grid on. X-axis I'm going to work in pi's. Pi over 2 with ticks. And so I'm going to type in the 4 sine theta, 4 sine x plus 3 cos times cos x. That was an equals, not a plus, wasn't it? No, that's it. So that's the graph we are thinking we've got. Let's try doing our 5 sine of x plus 0.644. And there we are, we've got the 2 graphs matched up exactly. Okay, so if I turn off the blue one, You see the red one. If I turn off the red one, you can see the blue one. Right, so that's the two things are equal. Let's do we want another one? I think there's a cosine one we need, isn't there? There we go. So, yeah, let's go for one more. Hopefully a relatively quick one. After Friday, I'm going to let you have a session just to practice any trig you need, and it will be a tutorial. Okay, so I'll just do one more on the express the following: the square root of 3 sine theta minus cos theta in the form of I wanted one where it was different. Okay, we'll have to leave that one do that for the moment. Unless I could find a quick tangent one, cos one. They normally tell you which form to do it in. Yeah, there's a cos one. We'll do that one. And there's a common follow-up question as well. So we're going to work in degrees. I want to express cos theta plus root 3 sine theta as r cos theta minus alpha. Notice they've given us a minus. This time this is the phase form, the alpha, where r is greater than 0 and alpha is between 0 and 90. Now, one thing to read from these is there are multiple ways of doing these. You can find, by changing the sign, you can get different r values. By finding phases in multiples of whatever frequency this is in, you can actually get more solutions. So this domain setting that they're doing in here is to make sure that we are giving the same answer they would like in their form. So the first thing we need to do is look at the equation, and we've got it in the form of r cos theta minus alpha. And if we borrow our equation from above, our identity, we can use that one to create this form. So from the identity we have it in the form of the negative. So this is the negative form, which means the sign there is going to be the positive. So we now have r cos, instead of a we're writing theta, cos alpha plus r sine theta sine alpha. And we do the same matching we did before. So my cos theta is here. So the coefficient of cos theta is 1. So r cos alpha must equal 1. I'll colour that again. So the coefficient here is, that's the red one, which is this equation, which gives me this conclusion. And if I go to the next one, I've got r sine theta sine alpha. Well, the sine theta is in my expression, so I get r sine alpha is equal to the square root of 3. And again, I'm going to just underline those bits to show which bits matched up. So root 3 sine theta gives me the r sine theta sine alpha. Equate the bits without the sine theta, and I get r alpha. Square both sides. Now, AQA used to insist that you didn't just take the two numbers and square them and add them together and square roots. They used to insist that you did r squared cos squared alpha plus r squared sine squared alpha is equal to 1 squared plus square root of 3 squared. And then this turns and gives us, they actually always wanted to see this line. And this is equal to r squared 4. And this now therefore leads to r is equal to 2 plus or minus. Because of the restriction they gave us at the top, r is positive, we want r to be 2. So that's me being particularly horrible and pernickety about the way I'm doing it, to say r must be 2. Remember that there are two solutions from the square root, so I had to choose the positive one. The cos squared alpha plus sine squared alpha, I don't think EdXL will ever insist that you are showing that line. But whilst you're practicing and practicing for yourselves, it will help reinforce where this all comes from. Do the angle side. We want sine over cos. So we want sine alpha over cos alpha. R in front of each, because we want to get the values correct. And that gives me root 3 over 1. And this will cancel down to give me tan alpha. Root 3 and 1, that reminds me of one of my triangles. So I'll quickly sketch my triangle. 1, 2, and square root of 3. The root 3 is opposite, so we're in the angle at the top there, the larger of the two. We're using radians, so how big is that angle in radians? Oh, sorry, in degrees. We're in the 60-degree angle. So we now know that alpha equals 60 degrees. So the final form, because they want it in that form, you should express it like that. Our final conclusion is 2 cos theta minus 60 degrees is the same as the expression they gave us above. Okay, flash your microphones if you're okay with that. Yeah, it's a really powerful technique. It's got its uses all over the place. This is the first section in something called Fourier Analysis, which allows you to analyse complex signals and break them down into different combinations of sine, cosine curves with different frequencies and different phases. But this is the first stage. Okay, off you go. Go and get some practice. We're in...
So can I just stop you for a second?
Yep.
So the class discussed if we could maybe slow down a little bit, because some of us are really behind with work. Some of the students are still working on the chapter review and then still working on the exercises from chapter 3.
Right.
And we are already halfway through chapter 4, so if we could maybe, you can give us a little more time on the exercises.
Yeah, you don't have, remember, you don't have to do all the exercises for me. I just want you to be comfortable. Yeah, but if you want to, yeah, I'm happy. I said Friday. Friday, I'll start. I said I was going to give you a chance with all of this to go through.
Okay,
Yeah.
great. Also,
Yeah.
what about the chapter review tests?
Which one we got?
Well, we only did chapter 1.
Yeah, we've got to do chapter 2, which was an intention for tomorrow. Would you like 2 days practice this week and we do another one next week? Chapter 2 we can do next week if you want. But I do need another grade in next week.
Yeah, I don't mind.
Yeah.
Okay, so you've got 2 lessons practicing with the trigonometric stuff this week. Can I then say we'll do chapter 2 review then on Monday?
Is it an afternoon lesson?
I don't think it is on Monday.
On Monday it's after lunch.
Oh,
It is, yes, it is.
Okay, great.
Yeah, so yeah, it's an after lunch one, so we can do it then. This will give me a chance to actually consolidate this down into a video as well. Okay, so all right, we'll give you 2 practice lessons now on all this trig for this one, and then we can look at the chapter 2 review next week. There is a reason I'd like some paces. If we don't maintain the pace now, we can easily run out of time going towards the exams. With what's happening about lockdown at the moment, I am worried that if we keep taking too many if I give you too long to consolidate things, we may not get through the course well enough. Okay, because I still want to give you plenty of time. Yeah.
Also, there was a question about when do you plan on starting the other 2 books?
Well, I was going to say, do you want to carry on with pure maths to answer Berger? And if you want to run straight through into P4, that we'll probably be starting that sometime during November. It'll probably be towards the end of November.
Is this mechanics or P4?
It's whichever. We should be finishing P3 mid-ish November for us to actually hit a time for you to get good enough practice for the exam. And they also want you to do some mocks at some point as well, which is why I'm worried about the timing a little bit. But yes, I'm happy for us to slow down. I'd planned on stopping at this point now anyway, but I'll give you 2 lessons now. We'll do a chapter review Monday and mechanics. Would you like to have a break between pure maths and do some mechanics in between, or would you like to do the mechanics after the pure? Mechanics is likely to be one of the first exams though.
We can decide later, can't we?
Well, Bozan's just asking when are we doing mechanics. I'm giving you the option of doing P4 then mechanics, or mechanics then P4. I can see benefits either way. If we do the mechanics after P4, we'll be running straight into the exam preparation time, so the mechanics will be fresh. But you've then got to practice your P3 and P4 a lot more leading into the exam time, or we can leave the P4 to last, because a lot of P4 will extend P3. So being able to do the P4 will help you with the P3. And then, so having a mechanics in between, then it's, would you like to do revised mechanics in a shorter time at the end? That's what we need to consider. So we'll have a couple of days. You can, by all means, message each other, talk about them. The information's there. I'm going to probably redo this video or try and slim it a bit because it did go on a bit.